We have been sold a lie about the path to artificial general intelligence. For years, the narrative was simple: build a bigger brain, throw more parameters at it, and a digital god would emerge. But behind closed doors, the giant labs have hit a quiet wall. Raw large language model reasoning is plateauing. Instead, a hidden architecture is taking over. This invisible layer has quietly become the actual operating system of modern AI, and almost nobody is talking about it. To understand the problem, we have to look at what a large language model actually is. Most people think of an LLM as an active, thinking agent. But in reality, an LLM is like a powerful CPU that has no operating system. It has no long-term memory, no file system, no concept of time, and no ability to interact with the physical world on its own. It is a frozen mathematical function. It only reacts when you prompt it, and the moment it finishes generating a response, it completely forgets you ever existed. To make this static brain useful, developers have had to build an incredibly complex software system around it. This is what systems engineers call the orchestration layer. Think of the orchestration layer as a massive shipping distribution center. The large language model is not the worker. It is just the dispatcher sitting in the tower. To get anything done, it needs a scheduler. In traditional computing, a CPU scheduler decides which software threads get execution time. In agentic AI, frameworks like Gradientsys act as the scheduler. Instead of just sending a prompt to an LLM and waiting for an answer, the scheduler manages a continuous execution loop. It takes a complex user request, breaks it down into subtasks, and decides which specialized models or tools should handle them. It runs tasks in parallel, checks for errors, and restarts failed processes. If a web search tool crashes, the scheduler catches the error, reroutes the task to a different tool, and keeps the agent moving forward without human intervention. This shift from simple prompting to dynamic scheduling is facilitated by emerging standards like the Model Context Protocol, which acts as a universal bridge between models and tools. For a long time, the industry tried to solve AI memory with a simple trick called vector search or retrieval augmented generation. Imagine giving a researcher a giant pile of documents and a filing cabinet. When you ask a question, the researcher grabs a few relevant pages, reads them, and answers. But this is not real memory. It is just search. True enterprise-grade agents need what researchers call a database-native memory substrate, a concept pioneered in frameworks like Oracle Agent Memory. This system does not just search static documents. It dynamically tracks the state of a user, remembers facts across multiple separate sessions, and accumulates procedural knowledge over time. It continuously decides what information is worth keeping, what should be discarded to save cost, and how to query that data instantly without slowing down the agent to a crawl. But giving an AI agent the power to run its own loops and access real-world tools is incredibly dangerous. In traditional software, code is predictable. If you write a loop, it executes exactly the same way every time. But because LLMs are probabilistic, the orchestration layer is highly fragile. An agent can easily get stuck in an infinite loop. It might call a tool, get a slightly unexpected error, ask the LLM what to do, and the LLM might tell it to call the exact same tool again. Within minutes, the agent can make thousands of API calls, racking up hundreds of dollars in cloud costs while accomplishing nothing. To prevent this, engineers are deploying defensive frameworks like AgentGuard. These systems act as real-time safety barriers, continuously evaluating tool calls before they are executed to block malicious workflows and stop runaway loops before they drain a company's bank account. This fragility highlights a massive contradiction in the current tech landscape. While consumers are experiencing AI hype fatigue, developers are realizing that making AI actually useful is incredibly expensive. In early 2026, a comprehensive study of thousands of developer repositories by Harness Engineering revealed a massive surge in configuration frameworks for coding tools like Cursor and Claude Code. Developers are desperate to automate their workflows, but the hidden tax of this automation is staggering. To write a single line of working code, an agentic framework might run 50 sequential LLM queries, cross-reference 3 separate databases, and execute 10 compiler tests. The orchestration layer makes the agent autonomous, but it multiplies the computational cost by orders of magnitude. The risks go far beyond runaway cloud bills. As the orchestration layer takes over memory management, it opens up entirely new attack surfaces that security teams are completely unprepared for. In May 2026, researchers introduced the MRMMIA framework, which exposed how vulnerable agent memory databases are to extraction and poison attacks. Because an agent dynamically updates its memory based on user interactions, a malicious actor can feed the agent a poison prompt. That prompt can be stored deep within the agent's long-term memory. Weeks later, when a different user asks a completely unrelated question, the poison memory can trigger, causing the agent to silently leak sensitive database credentials or execute unauthorized system commands. The memory that makes the agent smart also makes it a permanent security liability. We are moving away from the era of raw model scaling. The belief that simply building a larger neural network will solve reasoning, memory, and safety is fading. The true frontier of artificial intelligence is no longer found in the parameter size of the model itself. It is being built in the quiet, complex systems engineering of the orchestration layer. The companies that win the next phase of the technological race will not be those with the biggest brains, but those who design the most robust, secure, and efficient operating systems to control them.